original zeta function. And the rational function you obtain from the zeta function by replacing the variable by 1 over qt. But they are not the same. They are the same if you multiply some factor. This is the function equation. The last part of the conjecture is the so-called Riemann hypothesis. But I mean, it's not the open conjecture Riemann hypothesis. It's the Riemann hypothesis occurs over finite field. It says something about this polynomial P. We can find algebraic integers over 1 over 2g such that we can decompose the numerator as these 2g linear functions. In other words, I mean, of course, you can always do this if you do not require the algebraic integers. You can always decompose a polynomial with degree 2g into the product of 2g linear functions. But the important thing is that the absolute value of these numbers is equal to square root for all I. Okay. So this is, you can regard this as an analog of the zeta function hypersurfaces, because here, you know, this linear function, because this comes from the Jacobi side, so we have this fact. And we have a similar fact for zeta functions of projected curves. So this is the statement of the Weil's conjecture. And this is also the only theorem I will prove in this in this series of lectures. Before I start the proof, to mention a corollary and a remark. If you assume this conjecture, then we know that the zeta function is of this form, but you can expand this rational function as first you take the natural logarithm, and then you compare the natural logarithm of this rational function with this form of power series and match the corresponding coefficients. You will see that the number of fq to the m rational points on the projective curve C can be computed by this formula. Okay? And if you know this alpha 1 to alpha 2g, then you know all these numbers. In particular, if the genus is 1, you can show that here you have only 2 terms in this sum. And together with the Riemann hypothesis, you can see that this is always positive, this number. So that means on a genus 1 curve, you always have a FQ rational point, no matter what how large the field is. Even if it's very small, if the genus is 1, you have a rational point. That's the thing I'm going to mention immediately. I put it in the remark. Any other question? Okay, so this is the first corollary, and then I want to make a remark. I think I just actually the remark consists of 2 parts, and actually the rationality has nothing to explain. It just tell you the zeta function is the rational function. And for the functional equation, I just use FE to know the functional equation. It is equivalent to saying that this alpha, you can consider the same map. You map a complex number alpha to Q over alpha. This is the permutation of the sets of a 1. But here, this equivalence is true even if you don't know the Riemann hypothesis. Because if you know the Riemann hypothesis, you know that this alpha I times alpha I bar is equal to Q. And also, this is a polynomial with integer coefficients. So if alpha I is a root, or is the inverse of the root of this polynomial, then its complex conjugate is also the inverse of a root of this polynomial. But if you don't know the Riemann hypothesis, the functional equation just tells you that this map permutes these 2G numbers. Okay, this is what the functional equation says. The second part is the thing you just asked. Why is this called the Riemann hypothesis? Because actually here, for simplicity, I just define the zeta function in this way, but you can do a change of variables. I just replace in the definition of the zeta function. I introduce a new variable s, and I replace t, the variable t, by q to the negative s. S here is the new variable. Then the Riemann hypothesis is equivalent to saying that all the zeros of this zeta function should have real parts 1/2. Okay? Yes?
Is it possible that if the genus of the curve is very large, then there is no FQ point?
Yeah, it is possible, but yeah, probably we better discuss this after the lecture, because I think it will take some time to give such an example, explain why. But yeah, this is a good question. On genus 1, you always have a FQ rational points, but when the genus is larger, it is not necessarily true you always have a FQ rational point. Okay? So this is the relation, or this remark explains why the last part is called the Riemann hypothesis. You can regard as an analog of the real, the unsolved Riemann hypothesis. Okay? The $1 million Riemann hypothesis. Okay, so in the rest of the lectures, I try to give a proof of the whole conjecture. But before the proof, we need to make some preparation. And the proof will use some results in algebraic geometry. And if you are not familiar with algebraic geometry, my suggestion is sometimes you can make an analog between algebraic geometry and the context analysis. For example, the projective curves is analog in complex geometry, or complex manifold should be the compact Riemann surface. And on a compact Riemann surface, it has a very good property, namely the only holomorphic function which defines on the whole compact Riemann surface must be the constant function. In algebraic geometry, you cannot consider transcendental things. You can only consider rational functions. But you have a similar result here. On projective curve, the only regular function. Regular means locally defined by rational functions, but it is defined on the whole curve. Then the only regular function defined on the whole projective curve must be the constant function. We'll use this in the following proof. Today I want to start with the notion of divisors. I only talk about divisors on a smooth projective curve. So what is a divisor? Let's start from the definition. When the base field K is algebraically closed. This is not the object we want to study, because we want to prove the Weil conjecture for projective curves over finite field. But finite field cannot be algebraically closed. But for the definition, it is better to start from projective curves defined over an algebraically closed field. Then, on such a smooth projective curve, a divisor P is just a formal finite sum. E equals to sigma NP times P. Here, this P are just some points on the projective curve, and then you just pick some points on the projective curve, and you put some in here is NP, just some integers, and then you consider such a formal sum. But here you need to assume that it is finite, or in other words, for all but finite many 1p, this NP should be 0. Okay? So such a finite sum is called a divisor on the projective curve C. And as a notation, I use EIV C over K to denote the set of divisors on the projective curves. And clearly, such a set actually it is a abelian group, because if you have two such formal finite sum, then it is very easy to define the addition. And moreover, you can define the degree of the divisor to be just the sum of these coefficients. So the degree of a divisor should be an integer. And also we can introduce a partial order on the set of divisors. I say one divisor is bigger or equal to the other divisor if and only the corresponding coefficients have this relation. And P equal 5. And then I can talk about if a divisor is equal to 0, or in other words, all the coefficients here are non-negative integers, then we say D is effective. Okay? So these are some definitions. Then you may ask the question why we care about this looks stupid definition. The first one, the first answer might be because we want to count the points of k rational points on a smooth projected curve. K is a finite field. And then if, for example, if I know that the CFQ, the FQ rational points on the unprojected curves is given by P1 to P, for example, Pk. I know these points, and then I can take the formal sum of these points, and then it gives you a divisor. And if I want to count the number of FQ rational points of the curve C, then you just compute its degree. Okay? But then this is just you just play with the language. Because actually, if you already know the FQ rational points, this is a much more difficult question than just counting the kinetic number of these sets. Right? So I do not have time today. So in the next lecture, I will explain why we want to introduce the language of divisors, because it really helps you to count the number of these sets. And I want to leave you a question to think about at the end of the lecture. Here, I just give the definition of a divisor of a projected curve over an algebraic closed field. But if K is not necessarily algebraic closed, how can you define the notion of divisors, or the set of divisors? A naive guess is here, you just replace the point P by k rational points on the curve C. But this is not a very good definition, because on a curve, you may not have k rational points at all, or you only have 1 or 2 or very few k rational points. Then these sets can be very small. Then this divisor, the set of divisor, cannot help you much in the study of the curves. So you can think about how to define the set of divisors for curves over a field which is not necessarily algebraic closed. Okay, I'll continue with this tomorrow.